There are many different types of drugs, such as cannabis or alcohol, and we may have experienced their effects ourselves. But how do these drugs actually work? In this video, we will be discussing mechanisms of drug action. Psychoactive or psychotropic drugs act on the brain to affect mental state by influencing neurotransmitter signaling. To better understand how psychoactive drugs exert these effects, let's review the basics of neuronal communication at the synapse. Here, we see an image of two neurons, the axon of the presynaptic neuron on the upper left, and the dendrites, soma, and axon of the postsynaptic neuron on the lower right. Neurotransmitters are visible between the two neurons, triggering an action potential in the postsynaptic neuron. If we zoom in on the synapse, we can see the presynaptic axon terminal on the upper left and the receptors on the postsynaptic neuron on the lower right. Neurotransmitters, shown here as blue hexagons, are contained in vesicles in the axon terminal. When an action potential reaches the terminal, these vesicles fuse with the cell membrane, causing the neurotransmitter to enter the synaptic cleft where it can interact with the receptors on the postsynaptic neuron. While the image on the left indicates that the neurotransmitter is excitatory due to the depolarization it causes, it is important to remember that the specific effect of a neurotransmitter is dependent on the number and type of neurotransmitters and receptors involved. Psychoactive drugs work by affecting the communication between neurons and can be broadly categorized into two classes: receptor agonists and receptor antagonists. These two terms sound similar, but they represent opposing functions. Receptor agonists activate the receptor, while receptor antagonists inhibit activation of the receptor. It might help to differentiate the two by thinking that the words agonist and activate both have three syllables, while antagonists can be thought of as anti-agonists, in that they oppose activation of the receptor. This is similar to how the antagonist in your favorite book or movie opposes or acts against the main character. Now, it is important to note that I use the terms receptor agonist and receptor antagonist. This is because agonists and antagonists are best understood by their effects on the receptor, not the neurotransmitter, and some drugs may have different effects on different receptors. First, let's look at receptor agonists. These tend to act most similarly to neurotransmitters in that they activate the receptor. Again, we have a close-up view of a typical synapse, with the presynaptic axon terminal on the upper left and the postsynaptic receptors on the lower right. The neurotransmitter, represented as blue hexagons, is visible in the presynaptic vesicles. One of these vesicles has fused with the cell membrane, releasing neurotransmitter into the synaptic cleft, and one neurotransmitter molecule has bound to a postsynaptic receptor. Now, let's add in a receptor agonist. Receptors are specific to neurotransmitters, so receptor agonists tend to have a similar structure, in this case, green hexagons. The synapse is not sealed, so the agonist can move from the extracellular space around the neurons into the synaptic cleft, where it binds with postsynaptic receptors. Higher concentrations of the agonist cause increased receptor binding and activation. This holds true even if there isn't any neurotransmitter present in the synaptic cleft. So, receptor agonists activate receptors on the postsynaptic membrane, but not all agonists are created equal. On the left is a graph representing the membrane potential over time for a neuron during an action potential. In this case, the neuron begins with a resting membrane potential of -70 millivolts, and receptor activation causes a depolarization. When the membrane potential reaches the threshold of -55 millivolts, the voltage-gated sodium channels are activated, and an action potential is triggered. If we consider this depolarization and action potential to be the result of full activation of the receptor, then any agonist that triggers this level of response is said to be a full agonist. If we plot a vertical line representing the level of receptor activation with 0 at the bottom and 100% at the top, then full agonists fall at the top of the line with 100% activation. For example, morphine is a full agonist of the mu-opioid receptor, which is activated by endogenous opiates such as endorphins, causing feelings of euphoria and inhibition of pain signals. Morphine's efficacy for activating this receptor is what led to its medical and recreational use. If full agonists cause maximal activation of a receptor, then what about agonists that cause submaximal activation? These are called partial agonists, and they fall somewhere between 0% and 100% on our line of receptor activation. For example, buprenorphine also acts on the mu-opioid receptor, but as a partial agonist. As a result, it exhibits similar analgesic and euphoric effects as morphine and endogenous opioids, but at a lower level, making it effective for treating opioid addictions and chronic pain. Similarly, cannabidiol, better known as CBD, one of the main psychoactive components of cannabis, is a partial agonist for the serotonin 1A receptor. Serotonin is implicated in mood regulation, and activation of the serotonin 1A receptor can reduce anxiety, which may account for the perceived anxiolytic effects of CBD. It is important to note here that full versus partial agonist refers to the level of response exhibited by activated receptors, not how quickly or easily they are activated. To better understand this, let's consider the graph of membrane potential on the left again. If the endogenous neurotransmitter typically causes a depolarization that exceeds the negative 55 millivolts threshold needed to trigger an action potential, then a full agonist would likely exhibit the same effect. By comparison, a partial agonist would exhibit a reduced response, and the depolarization might not be sufficient to trigger an action potential. Now, you may have noticed that I said that receptor agonists tend to act most similarly to neurotransmitters. This is because, in addition to full and partial agonists, there are also inverse agonists. As the name implies, these are agonists that cause an opposite or inverse effect in the receptor compared to the endogenous neurotransmitter. If we plot inverse agonists relative to our line of receptor response on the right, they would fall somewhere below 0% in the negative response range. In our graph of membrane potential over time on the left, full and partial agonists both cause depolarization. By comparison, an inverse agonist would cause the opposite effect, or hyperpolarization. For example, while CBD is a partial agonist of the serotonin 1A receptor, it actually behaves as an inverse agonist of the receptor at higher concentration. Inverse agonists, however, are much less common than full or partial agonists. Now, when discussing receptor agonists, we looked at compounds that cause the receptor effect greater than 0%, including full and partial agonists, as well as inverse agonists that cause a negative or less than 0% effect. However, compounds that have a 0% effect cause inactivation of the receptor, and this behavior is exhibited by receptor antagonists. To best understand how this works, let's revisit the graph on the left, which shows membrane potential over time for a neuron. Receptor activation by neurotransmitters causes a depolarization, which triggers an action potential once the membrane potential crosses the threshold. The key concept here is that the initial depolarization is caused by activation of the receptors. In other words, a receptor must be activated before it performs its function. If the receptors don't activate, then there is no action potential. In essence, receptor antagonists function by inhibiting receptor activation. On the right, we have a close-up view of a synapse, with the presynaptic neuron on the upper left, the postsynaptic neuron on the lower right, and the neurotransmitter represented as blue hexagons. Under normal conditions, neurotransmitter is released from the presynaptic neuron into the synaptic cleft, where it binds to and activates receptors on the postsynaptic neuron. When enough of these receptors are activated, we get an action potential. A receptor antagonist, represented by orange triangles, can move from the extracellular space into the synaptic cleft, where it binds to receptors to inactivate them. When this happens, there are fewer receptors available for the neurotransmitter to bind to, which means that fewer receptors are active at any given time, and the overall effect on the neuron will decrease. As the amount of antagonist increases, more receptors are inactivated. If the concentration of antagonist gets high enough, it can inactivate enough receptors that the neurotransmitter can no longer trigger an action potential in the neuron. Antagonists are classified based on two factors. First, antagonists can either be competitive or non-competitive. This refers to where the antagonist binds on the receptor. Second, antagonists can either be reversible or irreversible. This refers to how permanently the receptor is affected. To start, let's look at competitive versus non-competitive antagonists. On the right, we see an example of a receptor. Every receptor has a binding site. In this case, the receptor is Y-shaped, with the binding site at the very top. This binding site is shaped like half of a hexagon, and it is designed to work with one or more neurotransmitters that share a complementary structure, like this blue hexagon and pentagon. However, competitive antagonists, like this orange circle, have a structure that is similar enough to the neurotransmitter that it can bind to the receptor, but not so similar that it causes activation of the receptor. When the antagonist occupies the binding site, the neurotransmitter is unable to bind to and activate the receptor. One way to think about this would be to consider two runners in a race, like these two stick figures racing towards the finish line on the right. Both are competing to reach the finish line first. In essence, this is how competitive antagonists work. If we replace the stick figures with a neurotransmitter and a competitive antagonist, then both are competing to reach the receptor first, and receptor activation depends on which one binds first. For example, the mu opioid receptor is activated by opiates such as morphine and fentanyl, shown here by the green hexagon and pentagon. In addition to causing euphoria, opioids also reduce breathing rate and blood pressure, and an overdose can lead to death by preventing the brain and organs from getting enough oxygen. Naloxone is a competitive antagonist of this receptor. If administered during an overdose, it competes with the opioids for receptor binding. This effectively reduces the number of activated receptors, which reduces the systemic effects of the drug and can prevent death due to overdose. However, large amounts of naloxone can overwhelm opioid receptors, causing withdrawal symptoms and preventing pain reduction by neurotransmitters. Non-competitive antagonists work a little bit differently. For example, let's consider the same Y-shaped receptor with the hexagonal binding site on top. In addition to the binding site, receptors may have one or more allosteric sites, also called regulatory sites, located elsewhere on the receptor, such as a little notch on the side of our receptor. These sites do not activate the receptor, but will actually regulate it. When a non-competitive antagonist, such as this orange triangle, binds to the allosteric site, it changes the shape of the neurotransmitter binding site from a hexagon to a square. Our neurotransmitters, which still have 5 or 6 sides, can no longer bind to the receptor, and therefore cannot activate it. If we go back to our example of two runners, this time represented as two neurotransmitters, the antagonist is no longer competing against the neurotransmitter to cross the finish line first, but actually changes the finish line to prevent the neurotransmitter from crossing it. Tetrahydrocannabinol, better known as THC, and CBD are both psychoactive compounds found in cannabis. However, while THC is an agonist of the cannabinoid receptor type 1, CBD acts as a non-competitive inhibitor of these receptors and reduces the effects of THC through these receptors. Antagonists can also be reversible or irreversible. This refers to how permanently the antagonist binds to the receptor. Most antagonists are reversible, meaning that the antagonist only temporarily binds to the receptor. This is true whether the antagonist is competitive or non-competitive. Competitive antagonists, like the orange circle, and non-competitive antagonists, like the orange triangle, both affect a receptor by binding to it. Reversible antagonists will dissociate from the receptor shortly after binding, leaving the receptor free to bind to another compound. However, irreversible antagonists form a permanent bond with the receptor, inactivating it entirely. When this happens, the only way to regain receptor function is by replacing the receptor entirely. For example, while naloxone is a reversible mu opioid receptor antagonist, naloxazone is an irreversible antagonist for the same receptor, which results in similar but longer-lasting effects. The reuptake inhibitors are a group of compounds that deserve special mention. To understand their effects, let's first review what happens when neurotransmission is terminated. On the right is our close-up of a synapse, with the presynaptic neuron on the upper left, the postsynaptic neuron on the lower right, and the neurotransmitter represented by blue hexagons. An action potential in the postsynaptic neuron will release the neurotransmitter into the synapse, where it can bind to receptors. However, the neurotransmitter will continue to bind and dissociate from the receptors as long as it remains in the synaptic cleft. To terminate this response, the neurotransmitter must be removed, and this is achieved in one of two ways. The first is through enzymatic breakdown, in which synaptic enzymes deconstruct the neurotransmitter. However, the neuron must constantly produce replacement neurotransmitters in order to keep functioning. The second way is through a process called reuptake. In this case, neurotransmitter from the synaptic cleft is taken back up into the presynaptic neuron to be reused. This is done using membrane transporters, represented here as green proteins on the presynaptic membrane. Neurotransmitters in the synaptic cleft can bind to the transporter and be moved back into the presynaptic neuron and into vesicles to be released again. However, reuptake inhibitors, represented here by orange circles, act as antagonists for these transporters, preventing them from moving neurotransmitter back into the presynaptic neuron. Reuptake inhibitors can be competitive or non-competitive, but in both cases the neurotransmitter is cleared from the synapse at a lower rate, resulting in a higher concentration of the neurotransmitter in the synaptic cleft for a longer period of time, which ultimately causes a prolonged effect on the postsynaptic neuron. Selective serotonin reuptake inhibitors, or SSRIs, are likely among the best known of these drugs. As the name suggests, SSRIs primarily inhibit reuptake of serotonin. Due to serotonin's involvement in regulating mood, SSRIs are commonly used to treat depression by prolonging the presence of serotonin in the synapse. Let's briefly recap. First, psychoactive drugs function by affecting neuronal communication, which is dependent on the type of neurotransmitter and receptor present in the synapse. These drugs largely fall into one of two categories: receptor agonists and receptor antagonists. Receptor agonists are compounds that activate the receptor and are differentiated based on the magnitude of the effect on the receptor. A full agonist causes full activation of the receptor, just like a neurotransmitter. A partial agonist, however, causes some receptor activation, but not as much as a full agonist or neurotransmitter. Finally, inverse agonists cause opposite receptor activity relative to the neurotransmitter. For example, if a receptor is normally excitatory, then an inverse agonist will cause an inhibitory response. Receptor antagonists, on the other hand, inhibit activation of receptors. Antagonists are grouped based on receptor binding. Binding can either be competitive or non-competitive. Competitive antagonists compete against the neurotransmitter for the same receptor binding site, and receptor activation depends on which one binds first. The ratio of neurotransmitter to antagonist determines which one is more likely to bind, which then influences the overall effect on the postsynaptic neuron. Non-competitive antagonists, however, do not compete against the neurotransmitter for the binding site. Instead, they bind to an allosteric site elsewhere on the receptor, causing a physical change that prevents receptor activation. In this case, the overall level of receptor activation is only dependent on the concentration of antagonists present, as the allosteric site can't be occupied by the neurotransmitter. Antagonist binding can also be reversible or irreversible, which refers to how permanently the antagonist binds to the receptor. Most antagonists are reversible, temporarily inactivating the receptor and then dissociating from it, allowing the receptor to bind with another compound. By comparison, irreversible antagonists form a permanent bond with the receptor, inactivating it entirely. Finally, reuptake inhibitors are a special group of antagonists. Reuptake is the process of moving neurotransmitters from the synaptic cleft back into the presynaptic neuron to terminate neuronal communication while maintaining a supply of neurotransmitter in the presynaptic neuron. Reuptake inhibitors function the same way as other antagonists, but their use actually causes increased activation of receptors on the postsynaptic neuron because the neurotransmitter remains in the synaptic cleft for longer. Selective serotonin reuptake inhibitors, or SSRIs, are a major group of antidepressants that function through this mechanism. Hopefully, this video has shed some light on the mechanisms of action through which psychoactive drugs work.